Ken's legacy shaped, not just who we are as a department, not even just who we are as a school, who we are as a university, but I would say, and things I continue to hear from Elizabeth, what the field is broadly. And that is a legacy that, I reflect on often, and I think this lecture helps us, sort of reflect on year after year. I remember Ken when he was a doctoral student, when I first started here on the faculty, and I remember him just striking me with his incisive comments, his extreme curiosity, his directness, his ability to put multiple fields and perspectives together and make something new. I was immediately drawn to him. Ken went from being a doctoral student to spearheading the Master of Urban Spatial Analytics program, really gave it intellectual architecture and focus. Ken, as you all well know and are the beneficiaries of now, Ken believed that data science belonged in the public realm. Students don't just learn to code or how to wrangle data. They use these tools to confront the most pressing issues in society, right? Climate, housing inequality, transportation, neighborhood change, and so on. Ken also understood the full life cycle of impact, right? That real change requires communication, right? And as someone who knew Ken for many years, it brings me multiple levels of delight when I hear students come back from PPA and say, Elizabeth is so amazing at teaching us data communication, because that is so integrated in the legacy of MUSA and what the whole sort of purpose of the program is today. He built MUSA around that. And, I think often, what would Ken think about where we are today? This program is incredibly thriving. Our students are doing incredible things while they're students and beyond. It's deeply integrated into the department and the school. And, that just, it gives me a lot of peace and calm. While my job is not to introduce Geoff, that's Elizabeth's, I will say that to me, something about this lecture that's really meaningful is that I think we invite people who are very much in the spirit of the way Ken thought about urban spatial analytics and urban data science. And I think our speaker today, Geoff Boeing, very well reflects that ethos and that commitment. His work in urban data science and geospatial analytics is, extremely rigorous methods in service of meaningful public outcomes. And I know I'm really looking forward to that today. So with that, I'll welcome Elizabeth to welcome Geoff, and thank you so much for being with us here this afternoon.
All right, thank you, Megan. I'm just going to quickly introduce our speakers so we can get on with the show. So it's my great pleasure to introduce Dr. Geoff Boeing, who is an associate professor at the University of Southern California's Department of Urban Planning and Spatial Analysis, and he's the director of USC's Urban Data Lab. He received his PhD in City and Regional Planning from the University of California, Berkeley, and his research and teaching focus on geospatial data science, urban networks, and information landscapes. His articles have been published in many leading journals, but of course his best articles have been published in the journal Geographical Analysis. I just had a meeting with our publisher this morning, and they let me know that his 2025 article entitled Modeling and Analyzing Urban Networks and Amenities with OSMNX was the most downloaded article of 2025. So I encourage you to go now and download that article, as well as many others from that same website. But after his talk. All right, so without promoting GA anymore, I am very happy to introduce Geoff Boeing to hear about his talk on urban networks.
Thanks, everyone. It's really an honor to be here. Ken was a big influence on my early career. When I started as a professor in 2018, 2019, he was willing to jump on a few Zoom calls with me when I was trying to figure out what like a curriculum looks like or what a syllabus should look like in this weird thing called urban data science that we were all kind of doing, but we didn't really have a good vocabulary around it yet. But I've always been really grateful to him for kind of working through those ideas when it was new to all of us. Yeah, so an associate professor at USC. I directed Urban Data Lab, and I'm also in the Spatial Sciences Institute there. And a lot of my work kind of intersect these different spaces, thinking about urban data from the kind of geographical sciences perspective. And in particular, today, I guess I should say I'm recently an associate professor. So this is kind of my first post-tenure project where I now begin to start throwing things at the wall to see what sticks. This is work in progress where I'm trying to kind of tease out some ideas and honestly some things that don't totally make sense to me. So I'd love to hear your feedback today about the extent to which it doesn't make sense to you either. So what I'm going to talk about today, I'm going to start off by thinking about this weird statement that a city is not a tree, and we'll think about whether or not that statement is true. And from that, or at least trying to figure out whether that statement is true or not, from that I want to think a little bit about the way that we talk about cities when we think about what cities are around the world, and this fixation on heterogeneity of cities. And I'm going to make a little bit of a counter argument this morning that perhaps heterogeneity is missing the point in certain ways, and that depending on how you look at cities, it turns out they're a lot more homogenous than at least I expected. And I want to take that back to a planning context at the end and think about why that would be, what exactly it is that planners do, and why they do it that way. So first off, a city is not a tree. So in 1965, British-American architect Christopher Alexander wrote a very provocatively titled paper called "A City is Not a Tree." And in it, he argued that planners often see cities or think about cities or try to plan cities to be these hierarchical tree-like structures. And you can think just like a tree in nature, right? There's a trunk, and then things branch off from that, and then branch from that, and branch from that. It's the opposite of like a crystal or a lattice structure, like a street grid, where everything is connected together. There's a lot of redundancy built into it, many different ways that you could travel through space. His argument was that during the era of high modernism, planners see and plan cities to be like trees. They're efficient, they're cost effective, and they're also really legible to top-down planning. Alexander's paper is interesting. I don't know how much of an influence it had in architecture, but certainly planners and urban designers have thought about it for many years. And in fact, it presaged a lot of the ideas that came out of complex networks and complex systems thinking in the latter half of the 20th century. Physicists love Christopher Alexander, but it's always kind of taken metaphorically. That is, cities literally aren't trees, but they seem to have something tree-like about them. At least some cities, maybe, sometimes kind of do. So what I was interested in, that kicked all of this off, was trying to measure that idea of treeness to see what exactly it is that planners do, or how tree-like cities actually are, and what kind of places might be more or less tree-like than each other. And so to take Alexander literally, there's this thing in graph theory, so the kind of the mathematics of networks, called a minimum spanning tree. If you think a graph is just a mathematical model of a network, a minimum spanning tree would be the minimal amount of network you need to connect every node to every other node by just one path, with no loops, no cycles. It's the version of a network with all of the redundancy, all of the options stripped out of it. And we can see that here. So in this image, I have some examples of small cities, street networks. In white, we have the minimum spanning tree. So that's the minimal network where you can get from all of the nodes That's like intersections and dead ends, to all the other nodes. And in red, you can see all the extra links in the full network. So those are the redundancies. On the top row, you have these kind of deformed grid-like cities with lots of red redundant links. Grids are really good for that. If something goes wrong, you have a lot of other options where you can travel to still get to your destination. And on the bottom, we have what are very tree-like cities. So often constrained by topography, like hillsides or cliffs. These cities will kind of snake into the valleys, and it ends up being that kind of branching form, street with branches coming off of it. So on the top row here, about 1/3 of the city streets are part of that minimum spanning tree. On the bottom, about 85% of the streets are part of that minimum spanning tree. So that means that on the bottom row, there's very little redundancy in that network. Sometimes cities are approximately kind of trees. So to formalize this, I wanted to look at a couple different measures of this idea of treeness in cities. And this matters for transportation planning, for evacuation planning, disaster management, transportation finance. Redundant networks are great, but they're really expensive. So I want to try to measure how much redundancy we have built into these networks. And so I have two measures here. We can think about redundancy in terms of length. So how many kilometers of network are in excess of the minimum you need to connect everything? Or we can think about it as links. So the link redundancy would be how many street segments or edges in the network exist that you'd have to remove until you stripped it down to that minimum spanning tree. So in graph theory, we call that latter one the circuit rank. That's how many links. And then if we normalize it, we say what proportion of the network are these excess links that need to be removed. So for length redundancy, we're basically looking at the length of the minimum spanning tree divided by the length of the original graph. And then this is the equation on the bottom for the circuit rank. It's the number of edges, those are street segments, minus the number of nodes, those are intersections and dead ends, plus the number of connected components. So that would mean like if your city has two disconnected pieces of it. And then you normalize it by the number of edges, and it tells you like 10% of the city streets can be removed before you get to that minimum spanning tree. So what we get when we look at these different indicators here is some relationships with other urban characteristics that I think make some amount of sense. So the y-axis here is our measure of treeness. So in blue, it's by length. That's the redundancy by how many like meters of street there are. And in red is that idea of the normalized circuit rank, or how many links, street segments are redundant. So more tree-like networks tend to have lower connectedness, or average node degree on the left. More tree-like networks are more prone to concentrated choke points. That's our middle plot here, the Gini coefficient of betweenness centrality. I'll talk about that in just a minute, but for now, what it means is something along the lines of how concentrated your network is into its choke points. And then on the right, we have circuity. So more tree-like networks are more circuitous. And you can kind of see each of those relationships here, where that bottom tree-like network has choke points, that is, the traffic funnels into one backbone arterial road in the middle of it all. It's more circuitous as roads kind of snake off into canyons or between hills. And it also is less connected. There are a lot fewer four-way intersections in those tree-like networks and a lot more three-way intersections as things branch. So if we look at this just as like a distribution of these values, what I was interested in is, back to Christopher Alexander's question, prompt, how tree-like are cities and do we see a lot of diversity in it? So these are just the probability densities of that length redundancy and that link redundancy, the circuit rank. Values closer to 0 are more tree-like. That means the network itself is more closely approximating its minimum spanning tree. And if we look just at this link redundancy, this is what share of edges need to be removed to produce that minimal tree, the no redundancy network. When I first saw this, the shape of this distribution was really interesting to me. And I'll say this is not what I was expecting to see when I started doing this analysis. And I wondered at first if I was doing something wrong. So first off, there are really thin tails on this distribution. And you tend not to see that a lot when you look at an analysis. In this case, this is looking at every urbanized area in the world. So we have about 10,000 cities here. And typically when you look at stuff across 10,000 cities, you see pretty long tails. That is, there's somewhere in the world that's very different than the average place in the world. You could think for the thousands and thousands of small cities and towns, there's going to be a couple of Tokyos and Jakartas somewhere that create a really long tail to the right. There are no outliers here at all. That is, this amount of redundancy in a network tends to be right around 30%, and almost all cities are between like 15 and 40% redundancy. Now, I think there's some theoretical reasons why that I'll talk about at the end, but the amount of homogeneity is surprising. That is, that there's no network that has a ton of redundancy. There are a couple of networks that get really close to kind of being a tree, but not quite. And the reason the homogeneity is interesting is because we always talk about heterogeneity as like the story of cities or how we understand cities. And certainly in my own work, what I tend to look at is trying to explain heterogeneity, to explain differences between places, either culturally or historically, or in terms of their outcomes, like walkability, the ability to adopt active modes of transportation. So in this figure, we have 4 city street networks, all held at the same scale of 1 square mile to be able to compare apples to apples between them. And you can really see how these street networks reflect different transportation cultures and planning paradigms and histories and cultural conditions and topographies. If you consider like the histories and values embedded in the classic street grid, from Hippodamus's early urban design work in ancient Greece to the Law of the Indies, the U.S. Homestead Act, the New York Commissioner's Plan. The grid has been used for centuries or millennia to express a kind of human order over the landscape, to make spaces more amenable to power and control or real estate speculation. And if you consider instead the autocentric form of U.S. Sunbelt cities and these ideas of privilege and exclusion that are very explicitly planned into different cities and suburbs around the world, you get these drastically varying levels of connectedness or accessibility or circuity in different kinds of street network designs reflecting all of those histories. You could think the extreme heterogeneity between the global north and the global south, very different modes of urban living, and how that both reflects the urban form and is reflected in it. And then, of course, as planners, we think about heterogeneity over time. So these are kind of median street network forms in the US in different decades, from the deformed and perfect grids in the early 1900s, to the winding, graceful embrace of the automobile around World War II, to the disconnected kind of dendritic networks of suburban cul-de-sacs in the 1990s. These networks look and feel very different. You can kind of guess more or less like when they're from and what kind of values went into their planning. One last thing on heterogeneity. So in a lot of my work, I'm interested in how planners create spatial order through design, in particular through street layouts ordering the city. And here this is a specific kind of order. In this case, what I'm talking about is the opposite of entropy in how we've oriented our cities. So entropy means something like disorder. So if you had a histogram, a high entropy histogram would mean that all of the bars are like the same length as each other, like an even distribution across all of your bins. Here I have a polar histogram for Manhattan to visualize that idea of order, like a regular histogram just wrapped around the face of a compass. So each of the bins are 10 degrees around the face of that compass, And in Manhattan, you can see that most of its streets fall into one of four bins: north, south, east, west, offset by 29 degrees from true north. There's some noise from things like Broadway cutting off from that, but we can measure that idea of how we've spatially ordered the city using entropy and these kind of histograms. So if we look at a different kind of planning paradigm here in Detroit, we have two different grids, one aligned with the waterfront, the older part of Detroit, and then one aligned with the national grid that was developed around it in the 19th century. And you can see those two grids pop out in its histogram, the larger one oriented on true north, and then the other one rotated off of true north. And we continue to see this heterogeneity, different kinds of places through this idea of spatial orientation. So here's Boston, which has a very different history. Not a grid-like city, but it has a couple grids in it, in like the Back Bay and South Boston. But what grids do exist there don't align with each other. And then a lot of Boston is former villages, 17th century New England pastoral communities that all agglomerated together over time. So, in terms of heterogeneity, I ended up looking at thousands of cities around the world. This is a sample of 100 of them, ordered from the most ordered on the top to the least ordered on the bottom. Chicago was the most orderly city. And as you'll see, the top couple of rows, it's a lot of North American cities built on that logic of the grid during the era of westward rapid expansion. A lot of European cities, Asian cities as you go further down, with one weird exception. In last place, the most disordered major city, Charlotte, North Carolina. We'll hear Elizabeth's ethnography of why that's the case afterwards. So, and a lot of this story is heterogeneity, right? You look at different cities, you travel to different cities, they're very different from each other. Much of my research looks like that, and a lot of the urban planning, urban studies research is predicated on that idea that places are different. When I was thinking about the spanning tree problem and the lack of diversity and redundancy in it, it made me start wondering that, depending on what we measure or how we look at it, it could be that places are much more homogenous than we think. And in particular, that could be explained by some fundamental characteristics of how cities are built and how planners go about their work in planning them. So my hypothesis here is what I'm calling this idea of universality, that cities could come from radically different parts of the world, or different time periods, or different planning paradigms and political cultures, but given a certain set of measures, they all converge on this narrow set of possible values. There's a wide range of things they could have been if we look at other networks in the world, even other networks embedded on the surface of the Earth. Cities tend to take on a very narrow range of those possible values, and I'm hypothesizing that we see that universally across several measures. So what I did for this project is I made a model of the street networks of all the urban areas in the world. There's about 10,000 of them. I removed the smallest one, so those will be like small town or villages, so that we're thinking more about urban agglomerations of, I think it was maybe 1,000 streets or more. And that puts us at about 6,000 total urban areas. And then I looked at a bunch of indicators of street network form for each of those cities. And then I calculated some measures of statistical dispersion for each of them. So basically trying to look at a bunch of different lenses to tell me, are these cities all kind of crunched close together in a really narrow range of values, or do they spread out and have long tails in their distribution? Let's try to answer that question about convergence. Do we make cities that in certain ways are all kind of variations on the same thing? So those 5 street network form indicators, we already saw the first one earlier. The normalized circuit rank is that idea of link redundancy. So how many street segments do we have in excess of the minimum we need to get around in the street network? The second one is circuity. So I talked about that briefly earlier, but here the way I'm defining it is how much longer the edges of the network are than straight line segments would be. So how much more are we geographically diverging from straight line paths? The average node degree is our measure of connectedness in the network. That tells us how many edges or street segments are connected to each node, so that's intersections and dead ends on average. So a dead end would have a node degree of 1, meaning there's one street coming out of it. That's what makes it a dead end. A four-way intersection would have degree 4. It's a degree 4 node. Next is the Gini coefficient of node betweenness centralities. So I mentioned that one briefly earlier, but that's our measure of the concentration of choke points in the network. So in network science, betweenness centrality is just a measure of how many shortest paths in the network rely on a specific node. It tells us something about that node's importance. So a node that a lot of shortest paths rely on is more important for efficient travel through the network. A dead end, for example, has very few paths relying on it, only ones coming from or going to that dead end. Conversely, if you have two sides of a city with one bridge linking it, all the shortest paths from one side to the other and vice versa rely on that one link, which means that it's a choke point and it has a really high betweenness centrality. Turns out if we take the Gini coefficient of that, that is, we look at the concentration of betweenness centrality values across all the nodes, it tells us how severe the choke point is in that street network. So that's what we're doing here. It'll help us identify things like concentration onto a single bridge. And then lastly, the average clustering coefficient is a measure of what we call in network science cliques. So that is a node has neighbors, the other node it's connected to. We look to see how close those nodes are to forming a clique, that is, all being connected to each other. In social networks, we tend to see that people's friends tend to be friends with each other, very clique-like networks. Well, without spoiling it, I'll show you what we see in street networks in just a minute. Now, what I wanted to do here is not only look at street network form, because I know, and I think most of you probably in the room are aware that cities are very, very heterogeneous by certain characteristics. So I wanted to make sure that we were able to look at a comparison case here to try to identify how similar or different those urban form measures are to some other forms of, some other measures of city size, like population and built up area. I'm also looking at average elevation and the population exposure to greenness in each of these cities. Now, these variables come from the global human settlement layer, primarily from remote sensing data to get stuff like the greenness exposure. The bottom 4 are city size indicators. A couple of them are related to the street network, so we have total street length and the total intersection count. But in reality, those are just measures of how big the city is. That is, we expect those to scale. Like Tokyo should have a lot more nodes than Des Moines, Iowa has. But I don't know if Tokyo necessarily has a very different average connectedness than Des Moines has. So for all of these indicators, I look at some measures of dispersion, and they will tell me about how concentrated cities are into a narrow band of values, or if cities take on all possible values all over the distribution. So I look at the coefficient of variation, which is the standard deviation divided by the mean. It just gives us a relative measure of dispersion that's commonly used in statistics. But it's not perfect. It's sensitive to the location of the mean. So I wanted to look at a few others as well, including kurtosis, which tells us something about the tailoredness of the distribution, so how extreme outliers are. The Gini coefficient, we talked about earlier for betweenness centralities. I calculate the Gini coefficient across the distribution's values to try to understand inequality. Are all of the cities in just one or two of the available bins, or are they spread out more evenly across all of the possible range of values? Shannon entropy, kind of similar. It tells us about the uncertainty across a distribution, so how close it is to being an even distribution. And then lastly, a simple measure of the presence of extreme outliers. So here I am using what are called Tukey fences, 3 times the interquartile range. It just means that any value greater than 3 times the interquartile range gets labeled an outlier. And then I'll just look to see what percentage of cities are outliers by that measure. So first off, These are my non-street network form variables. This is kind of the picture of what heterogeneity looks like in a statistical distribution. So we often call these scale-free distributions. That is, they don't have a characteristic scale. Calculating something like the mean for places like this can be weird because of the shape of these distributions. So they're something like a power law or a log normal distribution. What that means is, to take population, for example, in the top left. You have lots and lots of very little cities. That is, there are very many very small things. But then there's this long tail stretching out to like 40 million, where you have very, very few, very, very large things. So those are like Tokyo, Beijing, Jakarta, Seoul, like really big mega cities. And we see that kind of scale-free distribution in other phenomena in life. So earthquakes, for example, are a classic example of that. There are very, very many, very, very small earthquakes happening all the time to be imperceptible. And every now and then, there is a very rare but very, very large earthquake. So heterogeneity often means something like that. You don't have a characteristic scale. Cities could be extremely small, they could be extremely large. We also see that for greenness exposure. There are a lot of cities with really poor levels of greenness, a lot of brown and gray cities in the world. And then there are some that have a lot of trees and a lot of canopy coverage. Same thing for elevation. Most cities in the world tend to be built around sea level for the obvious historical reasons about settlement patterns, being near water, and so forth. But there are some cities built at extremely high elevation as well. There are some extreme outliers. So heterogeneity here, we see it in that right skew, really long tails, the presence of outliers. Here are the probability distributions of all those street network form indicators. The dotted lines I have on either side help you see the full range. So there aren't any outliers actually hiding that you just can't really see their bin. The dashed line in the middle shows you where the mean is. And if you look at these distributions shapes, there are no extreme outliers. There's really low kurtosis or tailedness. That is, they don't have long tails that stretch out in both directions. And there's really low dispersion. So they're extremely peaked among common values in the middle of the distribution. And what I did here is I tried to chop these plots at theoretical ranges where plausibly a spatial network could be falling. So for example, circuity on the far left. 1.0 circuity, the interpretation is that the city streets are twice as circuitous as a straight line would be. It's not terribly far-fetched. There are some pretty circuitous places in the world, and there are certainly individual streets that are twice as circuitous as straight lines would be, but there's nothing anywhere close to that on average across cities. Same thing for node degrees. 1 would mean the city is mostly dead ends. 6 would mean you have complex intersections like 3 streets coming together on average. But you see that on average, that just doesn't happen citywide anywhere in the world. Same with choke points, with our betweenness centrality. Cities are very similar with that 0.7 value. They tend to have a lot of concentration into choke points compared to most other networks you see in nature. Treeness we saw earlier, clustering coefficient, or being organized into cliques. Cities are strangely extremely unclick-like compared to almost any other network that you'll find anywhere. Here I've broken out those distributions by world subregion, and you can see that even across world subregions, the distributions are relatively similar to each other. That is, it's not like you have Asian cities on one side or African cities on the other side that are all getting agglomerated into one distribution. Even in different parts of the world, cities' average values tend toward the same convergence value. And then if we put it into numbers, sorry, the fonts made the spacing a little weird, but in orange, we have our street network form variables, and in white, we have those other urban indicators. And these are the different measures of like dispersion or extremity of values. So you can see in orange, they're sorted from biggest to lowest value. The orange are all on the bottom. Those are our street network form indicators with the lowest coefficients of variation. That is, there's not much variance in their distributions. Kurtosis is the same thing. They have much smaller tails, sometimes even negative kurtosis compared to other measures of cities. In fact, several orders of magnitude smaller when you look at urban form. Same thing for Gini coefficient and Shannon entropy. The street network form variables are by far the lowest dispersion measures by those indicators of dispersion. And then the one that was, I think, the most interesting to me was this idea of extreme outliers, because I think this is really what I'm trying to get at most clearly. This idea that by street network form, there just aren't outliers in the world. You can see for things like population, 7.7% of cities are outliers by that definition relative to the interquartile range. For many street network form variables, you see literally 0%, and for all of them, under 1%. So very few outliers exist in network form. Which brings us all back to this idea of universality. So the point I want to make with this, or I guess the way I'm trying to think about it right now, is that cities of drastically heterogeneous types and vintages and cultures all seem to converge on a consistently narrow and homogeneous set of universal indicator values for what their street network forms look like. So those geometric and topological forms are much more homogeneous than what we see for other things like city size, or how high they were built in elevation, or how green the city is. And what that means to me, because these are very different places in the world, that these urban form properties around street networks are independent of the underlying details of the system. That is, they're independent of politics or era. You get street networks that are similar to each other in a lot of ways, in spite of all of those differences from history in cities. So regardless of the location of the city or the size of its network, there is this homogeneity in street network form. And what that means, I think, at the end of the day, for planning, is that this idea of universality or convergence onto a narrow range of values means that many underlying planning processes and paradigms converge to generate similar urban forms at the end. So I want to take my last couple of minutes here and think a little bit about why this might be the case. So kind of speculating this part on the theory, because I don't have good hypothesis tests for these. Well, maybe for the first one I do. But trying to think about why we would see something like this in urban form that we don't see in other urban characteristics. So quasi-planarity is a fancy word from graph theory that just means that you have a network that is spatially embedded on a two-dimensional plane. That is, in our case, the surface of the Earth. Not really a two-dimensional plane, it's a curved manifold on the Earth's surface, but for all intents and purposes, it works pretty well. I say quasi-planarity. It's not really a planar network because we have things like bridges and tunnels. It's not perfectly embedded on that flat plane. Sometimes our lines cross each other in the third dimension. But when we do that, when we have bridges and tunnels, it's expensive. It's mostly a planar network because it's really expensive infrastructure to have it go non-planar in a city. As it turns out, that idea of spatial embedding and planar networks put topological constraints on what a network can do. By topology, I just mean the configuration of things in the network, so how they're connected to each other. And in particular, it sharply constrains the node degree of a network to be planar. That is, if you have a social network, maybe you have 100 friends, so you have connections from you to 100 people. Your node degree is 100. It's impossible to have a street network in which you have an intersection with 100 streets coming out of it. Because you're stuck in two-dimensional space, it's really hard to do more than like 6 or sometimes 8 streets coming out of it. So I think a lot of what we're seeing here for some of these characteristics are revealing something about the fundamental nature of building on the two-dimensional Earth's surface. That is, planners face constraints for something like connectedness, where they're working within a very narrow range of values that they have to work within physically, or at least financially. The second point here is around urbanization processes. So there's some interesting work about 10 years ago by a French physicist named Marc Barthélemy, where he looked in European cities at their evolution. He got time series data of how the street network evolved over time. And what he found is that the oldest parts of the street network today very closely resemble that network's minimum spanning tree, what we talked about earlier, that idea of a network with no redundancy in it. And so his argument is that those early networks are kind of like rural roads that become the arterials, and that urbanization follows a space filling process around it over the course of 1,000 years, and it retains that general overall structure. That is, that minimum spanning tree stays intact as arterial roads as time goes on. Given that finding, I think those kinds of urbanization processes, the way in which urbanization unfolds over time, can help explain a lot of what we're seeing, particularly for that idea of concentration into choke points. That is, as cities evolve around important streets, there are returns to scale of being an important street, and you just become more and more important as the city fills in around you. Obviously, that's not always the case. We have tabula rasa cities that we plan in some parts of the world. They don't always follow that pattern, but they follow somewhat similar patterns with road hierarchies. And that helps us to see a little bit about why the redundancy values that we saw exist, and why those concentration at choke points exist. And then lastly, I think a broader story about planning. Whether a street network is self-organized, whether it's been centrally planned, a lot of what we're seeing here is just an optimization problem. That is, something like redundancy is expensive. Something like having a bunch of bridges and tunnels is expensive. But they offer benefits. Bridges let you bypass things. It makes for more efficient links in the network. Redundancy is great. If there's an earthquake, traffic collisions, a flood, a mudslide, having more possible routes to get from point A to point B means you have a more resilient network. But we don't always build redundant and duplicative networks because it's really expensive to do so. And I think the argument that I want to make for some of what we're seeing here, the reason why we converge on a narrow range of values, is that they are roughly optimal values. That is, it is an optimization process in which we are trading off between the benefits of, say, redundancy and the costs of redundancy. And whether networks grow slowly over time with a many hands model, or whether they're centrally planned, top down, there is a little bit of this convergence toward optimality at the end of the day. Okay, so I'm gonna leave it at that. Like I mentioned, this is a work in progress. I'm still trying to tease out a lot of those ideas. I'd love any critical comments or ways that you can help me think about this as I proceed. Thank you very much for your time. I appreciate getting to be here.
Yep, we have a mic, so if anyone has a question, I can bring it over.
Thanks so much, Geoff. I really enjoyed your talk. I have so many questions and comments. I'm going to try and just keep it to a few. I guess the first one is about homogeneity and heterogeneity in general. The first images that you show of cities, I look at the maps and I imagine cities, and I feel like these cities are extremely different.
Yeah.
Rather than homogenous. So I was hoping you could talk a little bit about that. Another thing I was hoping you could maybe talk about a little is we don't connect links and nodes, we connect things along them.
Yeah.
So when you were talking about redundancy, in particular, the images that you showed that were more redundant, I imagine probably have a lot more households per amount of street.
Along the face of the
Yeah,
street, yes.
along the face. So I'm wondering, are they more expensive? Is it redundant, or is it connecting more things? And how do you think about that?
Yeah, well, in particular for that last point, I'm curious if you have any suggestions. This is what I'm trying to think through, because I feel risky sometimes talking about those streets in a grid being redundant, because those are the streets where life happens. That's where people live and where workplaces are. They're not just connecting intersections to each other. I think there is a safe or a valid conceptual framing around it of just being able to get traveling across a network rather than spending time in the stuff in the middle of the network. But I think there's a valid pushback from like a planning or an urban perspective against treating them as like discardable redundancies. So I mean, if anybody has suggestions, I'm trying to think about like what the framing conceptually would be for that. I don't know about like value of those kinds of places. It would be a good, I guess, economics question about how we capitalize the value of redundancy in land markets, especially if it does have like resilience benefits or evacuation benefits. I mean, you could see that really clearly if you look at the Pacific Palisades back last January versus Altadena. One of those was a lot easier to evacuate when the fire started than the other one was because of the presence of choke points. For your first question, yeah, cities are in general very heterogeneous. I think they're heterogeneous for the kinds of things that there isn't an optimum to converge toward. So for example, when we were looking at like the spatial orientation of cities, cities exist in every possible spatial orientation. They don't concentrate into a few narrow values. In some places they do. In the US, it's mostly grid-like for historical reasons. But in aggregate, if you look at, say, every urban street everywhere in the world, it's not a perfect even distribution. It's not the maximum entropy distribution. It turns out that even 5,000 years ago, people were orienting streets along with wind patterns for sunrise, sunset to maximize heat exposure in cold weather cities, to minimize wind, things like that. And so there, again, when there is that idea of an optimal value that you could converge toward, you still see that convergence overall. For things that I think don't offer that benefit trade-off that redundancy does or connectedness does, then you do see really long tails. Something like city size, there are all kinds of agglomeration benefits to larger cities. There are costs to it as well, and you end up with extreme long tails for it.
Thank you. It's really cool to see phenomena that don't follow a power law. There's so many of them. And you kind of alluded to the fact that cities are kind of weird in this way, and you don't necessarily see this kind of clusteredness in other natural phenomena. And maybe it has to do with quasi-planarity, but you can think of natural phenomena that are pretty much 2D. So is that something that we should not expect to see? Is there something that's really special about human organization in cities, or is it something that we just haven't looked in other places yet?
I don't know. It's a good question. Certainly very tree-like networks exist in nature. And they exist in cities too. So something like water pipes, for example, tend to be designed to be trees with very little redundancy. Electrical lines as well are often very tree-like. So what I've been doing for the first half of this project, thinking about trees, I've been going through databases of like graphs from like research databases that people assemble to collect graph models. And I've been calculating their measures, so looking at things like airline networks or bus routes, social networks, and just trying to understand to what extent cities are similar to or different from these kind of comparison cases. And they tend to be very different. If you have something like a bus network, it's different than an infrastructure network where you can have a really high node degree. That is, you could have, if you have like intercity buses, you could have a lot of buses that go between New York and many other cities, really, really high node degree. But you don't tend to have that for actual physical infrastructure on the surface of the Earth. Same thing for like airline networks as well. So partly it's that I'm looking at a narrow range of things here to make this specific case. You can find things that don't conform to it, both in nature and in cities, but at least for the certain street network form, it holds where we don't really see those same patterns elsewhere. At least I haven't found it yet, but maybe we do need to look elsewhere. If you find a good network data set, send it over.
Any other questions?
Hi, thank you so much for this talk. It was fascinating. I was wondering, like, if you've had any chance to look at the use of the streets, like, do people experience homogeneity to the same degree that the streets appear homogeneous?
Yeah, I have, but not for this project specifically. It's just one of the limitations of doing like the every city in the world thing. It's hard to, I guess I could do a case study. But we have looked at that for another project that I do where we look at the design of streets and the presence of amenities to understand the availability of being able to walk to meet your daily living needs. And then we work with local partners in those cities to actually measure people's walking behavior. And we do find relationships between the presence of pedestrian activity and things like the betweenness centrality of the street, even when controlling for the presence or absence of spatial amenities there that could explain why they're heading to that street. That is, that there would be like endogeneity between the presence of spatial amenities, the presence of pedestrians, and the fact that it's a high centrality road.
Thank you. This is very cool research. I wonder how you consider the three-dimensional form of cities and its impact on the two-dimensional pattern, because cities tend to look more different from aerial photo, bird's eye view than on a map. The three-dimensional form also indicates density, mix of use and population, etc. Right?
Yeah.
So the denser city, higher density city tend to have more redundancy on their local network than the lower density cities, which tend to be more tree-like, like the suburbs. So I wonder this might explain some of your inequality.
That's no, it's a good point. So I don't look much at the third dimension for this project, given that I'm looking more narrowly at network form. But I guess for network form alone, I do treat all of these as non-planar graphs to account for bridges, underpasses, overpasses, stuff like that. To your point, for like population and redundancy in a network, one thing we have found in the past, or I found in the past, was that there is sublinear scaling between population size and infrastructure amount in a city. So infrastructure scales sublinearly with population, meaning that the more people live in a place, the less infrastructure per capita there is. You can just think like New York versus Phoenix. It's a lot easier, but people can easily share the same street that's already there by building up into that third dimension. You don't need to have like a new meter of street for every person who moves to Manhattan. So yeah, there are certainly like efficiency returns to scale in that sense.
Thank you. Thank you so much for this, Geoff. It's fascinating, and my mind is spinning. I'm connecting it to something I've heard my entire career from airport directors, which is if you've seen one airport, you've seen one airport. And you know, I've always thought that it's a little bit of a leave us be, right? We're unique, and right, we can't be generalized, in that, you know, sort of the scholars I surround myself with, they're trying to push for, actually we can learn general things, and you know, there are these shared components. So I wonder if we sort of take it from scholarship to practice, what planners and public officials and so on would say, and that within the homogeneity, are there extremely different governance structures, or you know, are there things that even with these different governance structures we could learn, you know, safety patterns, and so, like you talked a lot about resilience and so on, and that there are, you know, there are interesting insights that we can gain. And even if you're, you know, a city with mostly DOT controlled roads, or a, you know, a city with, you know, locally controlled or council or so on, we can still learn from each other. It's not really a question, but I'd love to hear you surmise on this topic.
Yeah, no, I don't know. Well, this would be me prepping for a JAPA article then. I'll think, what can planners take away?
Exactly.
So one way I like to think about this, another thing in nature that shows similar distributions would be human height. There is a characteristic scale to human height. We have a meaningful average among humans. There aren't extreme outliers that are, many standard deviations away. However, height matters, right? It's hard to be an NBA player unless you're toward the higher end of the human distribution of heights. And I think we see the same thing in cities. So that there are big resilience outcomes if you just run like Monte Carlo simulations of disasters on different kinds of street networks. You see a big difference in outcomes for ones with choke point and ones that have like an even grid. That is, maybe their numbers aren't that different from each other compared to other kinds of networks that exist in nature without planar constraints. But within that narrow range of no outliers, some are NBA players and some aren't going to be.
Thank you for that.
There's the conclusion for my JAPA article.
Hi, thank you so much for your talk. I wanted to ask if you were using the city boundaries or if you were looking at something like a certain amount of density. It makes me think a lot about like LA's sprawl or,
Yeah. I'm glad you asked that. Yeah, it's a really important question. So one of the big challenges for doing this kind of international, like comparative morphology, is in having consistently defined boundaries. Otherwise, you're just comparing apples to oranges. So what I did for this and for all of this kind of work that I do is I use the global human settlement layers boundaries so that I'm not dealing with the problem of what is, New York City versus City of London versus City of Sydney versus City of Chongqing, all of which have very different definitions of municipality versus urban area. The nice thing about the global human settlement layer is whether I agree with its boundaries or not, they are at least statistically determined using this very consistent methodology that comes from remote sensing data. Comes from census data, it comes from governmental data about boundaries, and they put that all together into an algorithm that gives you the same definition of urban area everywhere in the world, discretized onto, I think, a 1 kilometer grid. So I used that to try to mitigate that problem of a city isn't a city everywhere.
Thank you.
Great talk. So actually, I shared this talk in my class. So a lot of students from my class may come here. So they may want to know some technical issue. So actually, I also have kind of question. Especially, you are doing great work and also developing popular Python module. I just wonder, can you just talk about some of your story behind the network X, NX, and also how you balance between doing great work and also developing software at the same time. Thank you.
My ringer I planted in the audience. Thank you for that question. The way I do great work, I'd say one hand washes the other is really the answer to that question. OSMNX, well, let me start at the beginning. I proposed a dissertation to my committee. It was going to be 4 chapters in which I was going to do this comparative urban analysis of networks around the world. They approved my dissertation prospectus, and a week later I started working on it, and I discovered that software that I thought existed somewhere to connect to the data set that I thought existed somewhere to let me do all of it didn't actually exist. So my dissertation transitioned a little bit into creating the software to allow us to do it in the first place. That's where OSMNX came from. It ended up just being a really useful tool to ask questions that I hadn't seen answered before in the literature because we didn't have, let's say, the right tool for the job. So a lot of my work over the past, I guess, like 10 years now has really been predicated on using that tool. And when I have a new research question I can't quite do with it, I just add some more code to it. And the benefit is that anybody else can then do it. Like it just unlocks it for other people who are interested in similar things. I get user contributions back from the community to improve the code base. And then the last thing, and Elizabeth and I talked about this a little bit at breakfast, but coding for me is thinking. I really like writing code by hand because it helps me try to solve problems that I don't like always handing off to ChatGPT to help me put together some code. Because I'm able to think through, like, what is the actual nature of the problem here? How do I want to represent it? How has it not been represented before? What can I do that's different? Why would it be better? What would be the limitations of it? And I feel like, my research has been better and more rewarding just because of that relationship going iteratively with coding. I would recommend it, though. I mean, everything's changing now with the value of open source code, how we develop it. But I strongly encourage people in grad school that if you do something where you have to write your own code to do it, it is a small, marginal extra effort to make it publicly available. You can have AI put together decent documentation for you at this point, especially using like doc strings to have self-documenting modules. Share it on social media. If you write a paper about it, make sure there's a link to your software. You can make a lot of other people's lives a lot easier, and then they like you because you made their life easier.
Hi. Thanks again for your talk. Echoing everybody else, it was inspiring. So I was curious, I'm assuming there would be a lot of technical challenges, namely data availability, to accomplish this, but do you see any value in exploring this question of homogeneity across time? As well as space? So do you, qualitatively, do you see evidence of like cities start out as less homogenous and then eventually converge on this practice? Or do you think that it emerges from like the very start and at what rate? That sort of thing.
That's a good question. From the empirical side, I don't think that's a question we can answer now, but we will be able to answer it 100 years from now, given when we have enough satellite imagery over a long enough time period. At this point, we can really only go back, I guess maybe 20, 25 years. And even then, the resolution is getting pretty bad in like the early satellite imagery. So 100 years from now, I don't know if I'll make it that long. Though given recent advances in medical science, maybe I'll be here 100 years from now to do some satellite imagery work. But at least empirically, I think there are some things that we just have to wait to see. And partly it's a little bit lost to history. We're able to reconstruct historical street networks in a lot of parts of the world, but not everywhere. And then there are all these sampling biases of what kind of places have historical records going back thousands of years. We can look at old Roman cities, Greek cities. There's a lot of interesting urban archaeology work. Folks like Mike Smith at Arizona State does interesting work looking at like urban street patterns in prehistoric cities. So where there are no written records of it, but just from archaeological digs, trying to reconstruct the network. And they find similar things to what we do today. There's a lot of grids way back when. They're aligned with things like sunrise and sunset. Or in hot weather places, they're aligned to increase like north-facing exposures to get more shade. That kind of like convergence toward optimality, where we do have case study evidence from 1,000+ years ago. We do see similar stories. But check in with me in 100 years. We'll see what the 22nd century city looks like.
Yeah, thanks a lot for your fascinating talk. I'm thinking that the road network are the most visible connections within the city, like people walk on streets, cars run on streets. But I think there's also some invisible connections within the city, such as some like social networks.
Yeah.
Or traffic flows. They may rely on the road networks, but they are not exact the road networks. Do you think we could measure them? And do you think there would be some sort of homogeneity in these for these connections?
Yeah, I don't know. The folks like Donald Appleyard did really interesting work. Kevin Lynch did stuff like this back in the 70s, 80s, trying to think about different streetscapes and what that meant for like the social networks in those micro environments of like an individual city block. I'm not a design determinist in general. I think that the urban form does shape some of our lives to a certain extent, but I'm also not a if you build it they will come person per se, largely because of self-selection biases. Not everybody, but a lot of people will vote with their feet to some extent about choosing a neighborhood that offers them the basket of amenities they want, including more sociable places or less sociable places. If you think of a place like LA, it really privatizes public life. You don't really have like pub culture or anything like that. When people socialize, they hang out in like their friend's backyard in LA. It's like house parties there. There's very little like street culture or bar culture, and partly it's because of the design of the streets. No one in their right mind wants to be spending extra time on the streets of Los Angeles. But also the kind of people who move to a place like LA move there because that's the kind of place where they want to live.
6.
One more thing.
All right, last one, and then we'll wrap.
Thank you so much. Wait. Quick question. I was wondering how like travel times or travel speeds might distort the lived reality of the street networks and how that might be reflected in like experienced homogeneity or heterogeneity.
Yeah, there are a lot of factors that influence travel time and travel speed. First and foremost, which mode of travel that you're using. Pedestrian speeds aren't affected that much by different street network designs. Driving speeds are drastically affected by different street network design. In addition to how many people live in that street network, if there's a grid with 10 people or the same grid with 10,000 people living on it. If they're all motorists, you're going to have very different congested travel times there. And then just like the traffic engineering problem of signalization looks very different if you have like a heavy minimum spanning tree, like a tree-like network with signal prioritization on that arterial, versus a grid of streets that are all equal in the road network hierarchy. You have a very different kind of signal prioritization problem that you have to optimize. So I guess, long story short, there's a lot of things that play into like the user experience of traveling on a street network. Like, what does the city provide in terms of safe sidewalks, protected bike infrastructure? Do they have legible, safe, efficient, timely buses? Or is it like anything goes, Mad Max driving around trying to get from point A to point B?
Thank you.
All right, thank you very much. I think that was
Thank you.